So it's very useful. It can do lots of stuff, but it has many warts and weird subtleties and inconsistencies, and you'll spend a lot of time on it. So at some point in your Coq career, that will be useful, but kind of amortize that time over getting useful work done. Okay, any questions about automation and such?
So when something like auto, is there a way to record the steps to solve and it can give it back to you?
That is a good question, and I think the answer is no. But before confidently saying no, I would want to check with super hackers. It would be very useful to be able to say auto, take the proof tree that comes out. I suppose you could just print the proof tree and then cut and paste it. But one would think there would be a better way than that, and I don't know. Yeah, that would be really convenient. Or like, why can't it just automatically, cache it in a file someplace so that when you change your definitions and it actually has to do the proof search, then it would do it and it would take 10 seconds, but every other time it would just look up the term that it found before. These are small matters of engineering that nobody's gotten around to.
What did you say, print proof? Is that show proof?
Show proof or just print at the end. All right. Let's talk about the simply typed lambda calculus. So this is kind of a case study now. So the lambda calculus that I'm going to talk about is the simply typed lambda calculus over the Booleans. So I'll have Boolean constants and I'll have a conditional. And my types are just two, Boolean and arrow types. And my abstract syntax of terms is defined that way. And as usual, I need this T cases stuff. Should be term cases, shouldn't it? Anyway. For helping with inductions over terms. Okay, now we need for the semantics a notion of values. So values are true, false, and abstractions. We need a notion of substitution, and this is the usual definition. Actually, there's a story about substitution, which is a long story, so let's not do much of it, but the short version of the story is substitution is a gigantic pain in the neck. It's one of the biggest pains in the neck. In fact, I'm tempted to say the biggest pain in the neck that one encounters when formalizing arguments about programming languages. And the reason is that the simple, naive definition of substitution, this one, is wrong. So you probably all know why it's wrong, but let's just review. So it's wrong because it isn't capture avoiding. So if I take a term with a free variable x, and I substitute it into an expression that binds x with a lambda x, where the thing that I'm substituting for, say z, the variable that I'm substituting for appears free inside of that binding for x, the x binding will capture the free x in the term that I'm substituting in. And that's wrong. It's wrong because it breaks a fundamental principle of kind of what variable names are. Namely, variable names shouldn't matter. So you should be able to consistently rename or alpha convert a bound variable without changing the meaning of a term. So if I change that lambda x to a lambda something else, now the free variable in the thing I'm substituting in isn't captured, and the resulting term means something different. It changes from a constant function to an identity function or something like that, or the other way around. So with capture non-avoiding, capture capture incurring or capture encouraging substitution, the invariance of all operations, in particular substitution, under renaming of bound variables is broken. Okay, so this definition is wrong. So what can we do? There are many possibilities, and none of them is completely satisfactory. So one possibility, the one that I'm doing here, obviously, is live with it. What could that mean? The reason that we can live with it here is that it so happens that we're only interested in beta reduction, call by value beta reduction of closed programs. So if you think about it, if you take a closed program and at the top level you have a beta redex, then the argument must be a closed value. So, and we're substituting now a closed value inside of a lambda expression with just one variable. The result will be something, again, closed. And so, kind of inductively, we will always be substituting closed things when we do substitution. And when we substitute closed things, capture avoidance is not an issue. So, in the special case where we get lucky and all we want is substituting closed things, this wrong definition happens to work. Right? It's good enough. And that's good because we can avoid a whole lot of fuss. So that's what we've done here. Where would that break down? Well, it breaks down almost immediately if you go in any direction. So, for example, suppose we wanted to formalize system F. It's the kind of next thing past the lambda calculus. This trick would immediately break because in system F, you have a typing rule that involves substituting for free variables. Which one is it? It's the type application rule. It's the one that says if you have a function that wants a type and you give it a type argument, then the type of the result is the polymorphic type with the type argument substituted in. So that substitution is performed during type checking in an arbitrary context. And the thing that you're substituting in may be a type with free variables. Okay, so this happy special case doesn't extend very far. What else can you do? Well, you can replace the you can replace the variable names by numbers, and there are different ways of doing that. They're all called some variant of de Bruijn indices, and that works, but it involves a lot of fiddly low-level incrementing and decrementing of numbers as you go through lambdas. So you can make that work. There have been some very pretty developments, even large-scale developments using de Bruijn indices, and people have succeeded in making it work. There's a general agreement that although it works, it's pretty clunky. So people are looking for alternatives. The current preferred alternative, in my mind, is the locally nameless representation. Which is kind of a hybrid. It uses de Bruijn indices for bound variables, and it uses alphabetic names for free variables. And there's a whole story about why that, although it's a little bit, the definitions are a little bit more complicated, it works out globally cleaner than the pure de Bruijn version. So there's the locally nameless. There's another one called locally named, which some people prefer. There are various forms of higher order abstract syntax. This is still actually a kind of active research area, and people are still making new proposals for how to best do this. Okay, so unless there are questions, I'm going to move on from that whole thing. Okay, so this is just something to be aware of. If you're formalizing larger things, you will need to deal with bound variables in some way. I currently recommend the locally nameless presentation, but recognizing that it's not perfect either. Okay, so that was substitution. Now, on top of substitution, we can define reduction. So in the ST-ABS rule, which is the beta rule, we're using the substitution operator. Aside from that, this is just standard Coq notation for a standard call-by value reduction relation. We're doing small step now, reduction relation. Okay, and then on top of that, if you like, we can define a multi-step reduction relation. This multi definition we skipped over, but it's just the reflexive transitive closure of a relation. Okay, now we have typing. And once again, we need to make a representation decision about contexts. So, and the two obvious choices are we can represent contexts as, well, maybe three choices. We can represent them as total maps, as partial maps, or as association lists. They will all get you there, but I find the partial map gives you the most elegant proofs later on. So context is a partial map that is a function from identifiers to options. The empty map is the partial map that always returns none. Extend is the function that takes a partial map and adds something to it, or perhaps overwrites something that's there. And then a context is a partial map where the range type is types of the lambda calculus. And now the typing relation is the standard one that you guys could all write in your sleep. And here's how it looks in Coq. And now we come to the interesting part. So here, for example, is the progress theorem. And then we're going to have a substitution lemma and a preservation theorem, as always. But rather than showing you the proof, why don't we take a pause at this point and do the proof? So let's see. Okay, so here's progress. Give it a minute to catch up. There we are. All right, so let's prove progress. So let's remember what progress says. It says if T is a term and capital T is a type, and in the empty context, that's all we care about because we're doing top-level reduction of closed things. In the empty context, little t has type big T, then either little t is a value or there's some little t prime that little t steps to. So how shall we start this proof? I'll do the first step. Okay, that's my contribution. Now, how does this proof go usually, by the way? When we do it on paper. Sorry? So we do induction of the typing derivation, and then in each case we get to use the induction hypothesis, which tells us that for all of the subterms, either the subterm is a value or the subterm can take a step, and then in each possible case, we have to figure out, well, that means that the whole term either is a value or can take a step. Okay, so how shall we begin, really? Induction. Induction on, what's it called? H. Okay. Oh, we've got a lot of sub-goals. Could we tidy this up just at the outset? Yeah. So we had this has type cases. And then we wrap the induction H in parentheses, and then since we're at the outer level, we want case instead of S case or SS case. Okay, this is a little bit better. So now each of the subgoals is telling us this is the T-var subgoal, et cetera. And now if I write case T-var, that will double check me that we really are talking about the T-var case. Okay, so now how do we prove this? Left, yeah, we certainly aren't going to succeed in showing that a variable steps. So we must have to show that it's a value. Okay, how do we do that? Well, I guess we'd better look back at our definition of value. Where was it? Here. Okay. Yeah, so there's something wrong here. So there's no way that the variable can have a closed type, or indeed any type. I mean, there are no variables in type. So there's no way that, to say it more carefully, there's no way in the empty context that a variable can have any type. So something is wrong. Because this is saying that x0, which is the variable we're talking about in the context gamma, has a type. That is, it's the result when we look it up in gamma is not none. So there must be something contradictory here, I guess. What is it? Yeah, so that's a good intuition. So where does that intuition come from? Maybe it comes from looking at the local context and observing that the thing we're trying to prove just doesn't look provable. Not inconsistent, but given just that gamma is an arbitrary context, and that looking up x0 in it gives us back a type that's perfectly possible if gamma is an arbitrary context, then we're stuck. Okay, so and the thing to notice is that some information got lost. Right? We started out with gamma being an empty context, and that fact is no longer present in our assumptions. It got lost along the way. So why did it get lost? So generalized dependent is the right answer, but to find it again. But why did it get lost? Let's look back here. So we did induction on H. H was not an arbitrary typing derivation. H was a typing derivation where one of the parameters was fixed. And the induction tactic was the culprit, was the one that lost that empty. So rule of thumb, never do induction on something that isn't completely, where the slots aren't uniformly filled in with variables. Okay, so we need to fill in that empty with a variable instead. How do we do that? Generalized dependent was a thought, but it's not quite the right thought. Remember. So remember empty as, let's just call it E. Okay. Oh, drat, that didn't quite work. Why can't it infer that implicit parameter? So empty, remember, is a function from, because the type of context is, well, sorry, the type of maps, of partial maps, is polymorphic. A context is a particular kind of partial map. It's a partial map whose range is types. But empty is a polymorphic constructor. So implicitly, there's an underscore following that empty, because implicit parameters was turned on when we defined it. And it's now failing to be able to figure out what type we intend in place of that underscore. So how do we fix that? At. So if we say at empty, that turns off the implicit parameter, and now we can explicitly supply the type parameter that we want, which is ty, the type of simply typed types. Okay, so now H is fully abstract. The E is remembered to be empty, and now we can try doing our induction again. Okay, does this look better? It does, because we still have that fact that gamma equals empty. Now, the fact that gamma equals empty is something we're going to want to use in many of the cases. And so, we needed to pull it out with this remember, but in some sense, the first thing we should now do is put it back in. So I'm going to suggest that in each of the cases, we do a subst E before we do anything else. Oops. Subst. What is it? Why didn't subst E work, actually? HEQE, sorry. No. Yes. Is that what I need to say? No, sorry. Yes. Okay. Well, anyway, that got us what we wanted here. Let's see if it gets us what we want in the cases to come. Okay, so now we're in the T-bar case. Let's go forward, and we do now have the information that we need to go forward, which is the fact that H is a contradictory assumption. So we're assuming that looking up something in the empty context, which is the constant none function, returns sum. So what we should use is inversion. Inversion H, or simply solve by inversion would work here too. Okay, and now we can see that we've gone on to the T-abs case. So what should we do in this case? So we need to know that either lambda blah blah is a value or it steps to something. I think it's a value, so we want to use left. Now, how do we show that it's a value? With VABS. And to avoid having to remember that, I'll bet we can just say auto. Yep. Because remember, every time we introduced an inductive type like value, we remembered to say hint constructors afterward, higher in the file. Okay. Yeah, probably would. Let's try. Yep. Okay, what about TAP? This is the interesting case, of course. So what do we need to do? Sorry? So we're going to prove the right branch, no matter what, because an application can always step. It isn't a value, so it better always be able to step if progress is going to be true. Okay, good. So now what? Now we need to provide a T prime. Where's it going to come from? From substitution, maybe, but not necessarily. Exactly. So we need to appeal to the inductive hypotheses, in general, both of them. Although there is one case, so we're going to need to extract the juice out of these inductive hypotheses. That's going to give us 4 cases, but actually 2 of them are going to be the same. Which 2? Right, so either T1 steps or it's a value, and either T2 steps or it's a value. So 4 cases, but 2 of them are going to require the same argument. Right. So if T1 steps, we don't care about T2. So really only 3 cases. So we should case analyze T1 first, because that'll allow us to collapse those other 2 cases. So how do we do that case analysis? So I heard destruct and inversion, and both of them are correct. So the exact difference between destruct and inversion is a little bit subtle, and I have started many discussions with Coq experts to try to get a really crisp explanation of when destruct is appropriate and when inversion is appropriate. And it seems that there is no crisp explanation of that. Here is the fuzzy explanation. Destruct is a much lower level thing. So it basically just corresponds to a pattern match on the inductively defined data. Inversion is a much higher level thing. The proof term that it generates is some big hideous stuff. And it's doing a lot more for you in terms of generating equalities and things like that. So a rough and ready guide is if you care about the proof terms, if you're going to be looking at them, try to use destruct, probably never use inversion. Usually we don't care about looking at the proof terms, so then basically you could almost always use inversion, except there are a few times when destruct is actually more convenient, and it happens that this is one of them. And here's why. If you say inversion, it's going to fail. If you say inversion on this hypothesis, it's going to fail. And the reason is that this hypothesis does not have an inductively defined type. Right? It has a pi type because of this trivial assumption. It's possible to deal with that. So we can, for example, assert a little local lemma that empty equals empty, and then use apply in to get rid of this, and kind of peel off this part. That will work. Oh, you might think, why do I even need apply in? I could just, if I had that lemma, I could just apply IH has type 1 to that evidence, and then apply inversion to that. And that won't work because inversion demands that it be applied to a variable. So it's one of the few tactics that you can't just apply to an arbitrary expression. It needs a variable. Okay, so you have to fiddle around a little bit. It works fine. I did it this morning. It takes a couple of lines. But actually, in this case, destruct is more direct because destruct is smart about conditional facts. So if you say destruct to a conditional thing, it will destruct this, and this will become a subgoal that has to be proved. So in this case, destruct is a little bit simpler. So let's do destruct IH has type 1 and see what happens. Okay, so the first thing that happens is we get this trivial hypothesis that has to be discharged, and fortunately that one is, I think, is easy for auto. Okay, so now we have the interesting information that okay, so now we've generated two subgoals, one for the case where T1 is a value, and one for the case where T1 steps. So we're looking now at the T1 is a value subcase, so let's remember that. And now what? Now we need a case on T2. So we'll do it the same way. Oops. Okay. All right, so now we're in the sub case. Sorry, not what I meant at all. I'm sure that's going to confuse proof general terribly. So let me roll back to here and then roll forward again. By the way, I'm sure you've already discovered, if your IDE ever gets desynchronized from the underlying Coq interpreter, just go back a couple of pages and then go forward again, and it almost always fixes it. Occasionally, you have to kill off the underlying interpreter if things get really confused, but that almost never happens to me. Okay, so now we're in the case where they're both values. And now what do we do? So here's the point where, so we know that T1, we know that we're in the beta reduction case. So we need to construct the T prime. And what do we need to construct it out of? Yeah, so we know in our hearts that T1 is a lambda. We need to get Coq to understand that T1 is a lambda. How can we do that? From its type would be a good way. And so what would be a good tactic to try for that? Destruct might be a good one, or inversion. I'm actually not sure which will work better in this case. I think this morning I tried inversion, but let's try destruct now and see what happens. So destruct H. So that probably gives us several goals. Ooh, that gave us a bunch of new goals. But maybe a lot of them are trivial, so let's have a look. So this must be the variable case, yes. So this is the case, look at H1, where we have some variable x0 and it's a value. Oh, but that can't be, that's a nonsensical case. So perhaps we can, and a bunch of the other cases are going to be nonsensical too, right? So there's going to be a case where T1 was true, a case where it was false, a case where it was if. All but one of the cases should be nonsensical. And so we should be able to deal with them all at once if we can figure out what's the right tactic to do it. So what is the right tactic? Okay, let's try it just once and see what happens. Did that deal with that case? Yes. Okay, so that seemed to work, so let's be more ambitious and put it after a semicolon. So at this point we have 6 subgoals, and at this point we have 8. Okay, so it seemed to deal with maybe all but one of the extra cases. Let's keep needing to make this window bigger. Okay. What do we need to do at this point? Where are we? Well, we do seem to be in the T-abs case. Here's the thing that's a value. And so we should be close to our goal. There are some kind of silly equalities in the context. So I'm going to suggest that we just substitute those away before we do anything else. And now look at it and try to think. So what do we want to do? So we have now the lambda that we wanted. So it's time to construct T prime, I guess. And T prime is going to be the witness for the existential. So now it's time to basically apply the existential introduction rule. Anybody remember which tactic that corresponds to? Exists. And exists has to be supplied with a value for T prime. And what's that value? So it's the body of the lambda, which is little t12, I think. T0 is the type. So it's t12, and then we substitute, and that was the notation we made up for substitution. It was x0 colon equals, and then what gets substituted in? T2.